So now this is like very scary, right? You've got process A, B, you've got process B, C, and C, D, and then D, A, and we're back again, okay? Now, another thing to think about on this type of graph, right, is that every pressure and volume corresponds to a temperature, right? Because PV equals nRT, right? And so therefore T is equal to, what is it? It's equal to PV over nR. Well, N and R stay the same. P and V change, but if P and V are the same, right, this corresponds to a particular temperature. That's another temperature, and possibly another temperature here. Okay, so this engine goes all the way around. We start and stop at the same temperature. Therefore, the internal energy must be the same, right? Okay, and so the way you solve these things, of course, is that we just add up all the work. Okay, now A to B has zero amount of work. Heat flows in. There's positive heat flowing in because we're raising the pressure, but not letting the piston move. But work is zero. Okay, the work is also zero for this guy, right? Heat is actually flowing out of it, right? It's got a negative heat because we're letting the pressure drop. But we're not moving the piston, so it must be getting colder. This must be hot, right? This has got to be colder, right? Okay, so this work is also zero because the piston doesn't move. Remember that work is pressure times change in volume. There's no change in volume on CD or AB, right? So if we want to find the total work done, we're just going to add it up, okay? Process AB, okay, work is pressure change in volume, right? But the change in volume is zero, so it's 0 joules, right? For BC, well, it's a different story, right? It's pressure change in volume, and the pressure is 500 pascals, and the change in volume here is positive, let's see, 1, 2, 3, 4, 5, positive 0.5, right? Cubic meters, and the same as this is negative 0.5, right? So positive, right? And that is positive joules, right? Okay. And then CD, process CD, the work is also equal to 0 because the piston doesn't move. There's no change in volume. And then DA, process DA, is equal to the pressure now is 200, right? And the change in volume is negative. This change in volume is negative 0.5 cubic meters, right? So it's right, and that is what is that, negative 100? Now, if we look at this thing, if we add up all this work, and that's the question, right? What is the total work? If we add up all that work, we get 0, right? Plus 250 plus 0, right? 0 plus 250 plus 0 plus negative 100, right? Still equals positive 150 joules. So this is the marvel that is a heat engine, right? Where did that work come from? Well, it came from a net amount of heat flowing into the engine that didn't flow out, okay? More heat flowed in than flowed out. 150 joules more flowed in, okay? So this heat engine turned heat into work. How did it do that? Well, it's very simple. When it moved out and did positive work, it did it at a higher pressure. And when it had to move back in at a lower, it did that at a lower pressure, okay? And so it did, the world did less work on the engine than the engine did on the world. Now, how do real heat engines do this? Your car has actually a compression stroke, right? But it does that at a low temperature. So when the piston moves in your car, it's doing that at a cold temperature. That's cold stuff that goes in there. And when, of course, the piston moves out, it's doing it at a fiery hot temperature. Right? So we manipulate the temperature. In your car, it's done by very simply by combusting the gas in the cylinder. With a steam engine, the steam engine piston moves in and it pushes that steam out into the air, which is at a low pressure. And then when it moves out, that steam that's coming in is coming in from the boiler at a high pressure. Right? And then if you there are cars. I think the Mazda RX-7 has I think it's a rotary engine or something like that, a Wankel engine, and it actually has an air conditioner to make this, when it compresses like that, it makes that compression happen at even a lower temperature and a lower pressure, because obviously the bigger this thing is, the higher this line is and the lower that line is, the more work you can get out of this. Okay, now I'm going to show you another way to do this. Okay, is you can also look at this thing and look at the area inside this. This area, okay, equals length times width, right? That area is equal to the work, right? So just for example, okay, this thing measures 1 to 300 pascals, okay, and then this is 0.5 cubic meters is this dimension here, right? And this is 300 pascals there, and of course work equals area equals length times width, so it's 300 pascals times 0.5, and this always works, right? It's 150 joules. So the area inside equals work, okay? And then how do you know whether it's positive or negative? Well, if you draw your graph this way, as everybody does, right? Positive, if it goes clockwise, then it's positive work, okay? And of course, if we reversed everything and we had it compressing at high temperature and going out at low temperature, right, then anti-clockwise or counterclockwise, right, would be negative work. Okay, the Brits say anti-clockwise, and I'm trying to get you used to that because you'll take a British test. Okay, so that's the other way to do this thing, is to just look at the area inside of that thing. Clockwise is positive work, or in general, just remember if it moves out at high pressure, right, it's doing more work on the world, and if it moves in at low pressure, the world does less work on it. Okay, so that's the other way to do this. Here's a diagram of an actual heat engine, and I've got a little steam engine that I'm frankly quite afraid of, right? But the way this thing works is that we've got this is our high pressure, this is low pressure. Okay, and what we do is that at a particular instant we've got a valve here that closes. The high pressure steam is allowed to go in here, right? It pushes the piston out. Literally, it drives the wheel around. The piston's actually attached to the wheel, which I think is rather remarkable on a choo-choo train, right? Okay, the wheel goes around. Of course, you got a flywheel on here that's got some momentum, and then a little bit later, you know, as soon as it comes around and it's going to push that piston back in for another kick, we close this valve and open this valve. And as the piston moves in, this gas goes in here into something called a condenser. Heat has to flow out of it to condense. Okay, so heat flows out of that condenser, and eventually it condenses. The water condenses into the steam condenses into liquid. We've got a little pump that'll pump it back in here. You can also just vent it into the air, but then you have to you use up a lot of water like that. Okay, I've got a demo of this, so this is a very cool thing. And then this is something called a Sankey diagram. Okay, and usually they're drawn with like arrows like this, like that. Okay, but the idea is that heat flows from the high temperature, and in the book they have QL. Here in the data packet they'll have QC and temperature cool like this, right? But all heat engines waste a bit of heat, and here is why. Okay, if you look at this thing, this process here, this is heat flows in, right? Because if you look on this part here, the piston doesn't move, but somehow the pressure increases, right? Well, the only way to do that is to have heat flow into the gas, right? And then again here, we're allowing the piston to expand, but the pressure should drop, and it doesn't. The only way to do that is to raise the temperature. So T increases here, right? Heat also flows in here, right? Okay, but now we're here, right? The piston's all the way out, and now we need to repeat the process, right? Now, to be sure, you know, no process is actually this perfect square box, right? But let's just go with it, okay? Well, the only way to make the pressure drop so that you can move the piston in is to have heat flow out, right? Okay, so this is minus Q, heat flows out. And then again here, we're moving the piston in, and the pressure really should rise. If you move a piston in, the pressure should rise. It doesn't rise. The only way to do that is to drop the temperature by having heat flow out as well. Okay, so they all engines like that, and there's a law, the second law of thermodynamics says you can't actually turn all the amount of heat into work. It's not possible. Okay, it would be possible if you could reach absolute zero. If you could make your cold temperature reservoir absolute zero, you could do it. And we don't study those equations anymore in the data packet, but that's the notion. Okay.